All right, let's get started. It's Friday. All right. Does it feel like Friday? Okay. Oh, okay, good. So today we are not going to do OS 161 help in the middle of class. We are, you guys are welcome to work on the assignment, just like somewhere else. All right, so today we're going to talk about files. So we're starting our unit on the disk and file systems, and we're going to sort of take the same approach that we've taken with other parts of the system. We're going to start by talking about an abstraction. So we're going to talk about the file abstraction today, properties of that abstraction, and get into a little bit about how file systems provide the abstraction of a file, and also try to sort of unpack a little bit of the assumptions that you guys are used to about files, because files are a part of the system. I mean, you know, how many people have used a file? Okay. How many people have knowingly swapped a page to disk? So yeah, so the files are a little bit more visible to computer users than some of the arts, or how many people have noticed their program doing a context switch. Well, maybe you can notice that, but so files are a little more visible. So you guys think you know something about files, and to some degree you do, but you know, we're going to talk a little bit about where your ideas come from and what's important about them from the perspective of file system design. All right, so as you guys know, I think by now assignment 2 is due on Monday. We are adding some office hours on Monday night to help with last minute, you know, like helping you just like, you know, improve performance of your exact implementation, or, you know, just optimize fork a little bit more, you know, maybe add support for the open flags to open, things like that, right? So Monday night, calendar's up to date. I think Jing Hao has volunteered to be here till 9, and then John Gerber will be around late, and I may be here too, and maybe we'll get some pizza at some point. If anyone is brave enough to try to implement open flags, how about that? All right, so any questions about disks, about the parts of disks we talked about on Wednesday? Let's do a little bit of review. What is the platter? Draw a platter. Yeah, there we go. It's a circular thing, right? It's the part that the disk is made of. It's the circular flat disk on which the magnetic data is stored. How about the spindle? Draw a spindle. This thing. Yeah. Be careful which finger you use. Yeah, it's the drive shaft. Platters are attached to it. What about the head? Yeah, it's that thing, right? Your little comey thing. Actually, that's the arm, right? The heads are actually mounted on there, right? So the head is the sensor and actuator that actually reads and writes magnetic data onto the disk, right? How about locations on the disk? Who can make a track sign, like a, yeah, like that, right? It's the track is it's the lane on the racetrack, right? Except it's circular. Some of you guys probably are used to, I don't know. This is not Indy 500. This is a circular. That'd be kind of a boring racetrack, right? If it was just going in circles. What's that? NASCAR. Yeah, but that's the thing. NASCAR is not circular. It's like an oval, right? So imagine circular NASCAR as the track. Goes in a circle. Sector. Any remember this? Yeah, it's the pie part. So it's one sort of, there's a name for that. If I was a geometrician, I would know what it is, but I don't. So it's just the pie slice thing. What about a cylinder? What's a cylinder composed of? Yeah, I mean, it's sort of the vertical intersection of the cylinder with all of the disk platters. Right? Why, just, you know, as a quick quiz, why is a cylinder interesting? Why is it interesting enough that we have a separate name for it? Yeah.
Because you can read and write data simultaneously in a cylinder.
Why?
Because the heads are all lined up.
Yeah, so on most disks where you have one arm with a bunch of heads that are reading and writing from all the platters at once, the cylinder represents all the data that can be read and written to the disk, or all the locations on the disk that can be read or written to without moving the heads, right? And this is why there are file systems that we will look at that pay attention to what are called cylinder groups, right? Or groups of tracks that are close together on the disk. All right. So we talked about ways that disks are different They move, they're slow, and they're devices, right? And we remember the steps to write to the disk, right? And this, we'll come back to this. So I have to issue the command. I have to get the heads to where they need to go, right? That involves moving the arm. That's one of the slower parts. Wait for the heads to actually settle on the track so that I'm writing in a straight line and not a squiggly line. Wait for the platters to rotate the data I want underneath the heads. And then finally, get the data back from disk to the operating system, usually into memory. Right? All right, so disks are getting blank, but not blank. Larger, but not that much faster. A little bit faster. Now, Flash, again, Flash changes this a little bit, but Flash means disks aren't getting larger anymore. They're just getting more expensive. But quite a bit faster, right? All right, any other questions before we go on? Yeah?
Does each track on a platter have the same amount of data?
Ooh, good question. Does each track on a platter have this? What do you guys think?
No.
Why not? Yeah, so the ones on the outside are longer, right? What does that also mean about the outside of the disk? Well, it doesn't take longer to get around. Yeah.
You have a higher data rate at the outside of the disk.
Indeed. You have a higher, you can read and write faster to the outside of the disk than the inside. Because there is more, the disk is spinning at a constant RPM. Every track is spinning at the same speed. But the amount of data on the outside tracks is more, meaning that there's more data passing under the heads than on the inside of the disk. So a lot of file systems will lay out data starting with the outside of the disk because it's faster to read and write to. Again, disks.
What's like the magnitude of the number of tracks per platter?
I wish I knew this. It's thousands probably. Yeah, I don't think millions, but a lot. Yeah.
There are sectors on disks, right?
Yeah.
Are those slices, or are they different sets of tracks?
I think the sectors that we've defined it as a slice. Right? I don't know why that's interesting, though, to be honest with you. We're quite understood what's interesting about sectors.
Yeah, I was just wondering, how does it know where it is? How does it control the spinning of the platters? Because that's you need extreme precision to spin something to the right place.
Yeah, well, remember the platters are spinning at a constant rate, right? The platters, when you buy a disk, it comes with a particular RPM. The platters don't ever change speeds, right? They're always spinning, right? And you want them to be spinning at a pretty fixed RPM, right? If you're asking how you get the heads to settle in the right place, that's a separate question.
That also means the heads have to go read and write at different rates.
Yes. Yes. In fact, yes, that's true. Actually, so we'll come back to this later, but there were early disks where the heads actually could read faster from the disk than they could transmit the data back to the system. And so this caused these weird issues where you could read a little bit of data and then the buffer would get full and you couldn't keep reading. You actually had to stop, wait for the buffer to empty, and read again. And there were file systems that actually laid data out on the disk in chunks so that you could read a bit of a file, stall, read the next bit of a file. Because otherwise you have to wait all the way until you come all the way around. Right? Oh, terrible. Just nastiness caused by disks and their weird features. All right, any other questions? Good questions. All right, so let's talk about what files are. And I think it's important to just be sort of precise about what we mean about file and about file semantics, right? So today we'll talk about a little bit about just what a file is, right? Files themselves, right? I want to mention a little bit, because this is kind of increasingly important, about storing information about file contents, right? Because there's some interesting design decisions about how file systems do this. We call these attributes. And then, so the sort of how does Unix file system manipulate, well, how does the Unix interface manipulate files, and what sort of relationships or information does the operating system have about what files are being used by each process, and then also organizing files, right? So how do I organize files into some sort of namespace so that that's useful to users, right? All right, so at minimum, what does a file have to do to be useful? Early file systems did little other than this. Let's do store data. I would add another word there. Okay, that's part of it. So reliably store data, right? Not just a little bit of data, not sometimes, right? Not once in a while when you get lucky, you know. Not only every other byte or whatever, like not only for a few minutes. You know, reliably store information, right? Yeah. Yeah, it should only change in predictable ways. That's a good point. And I think that's part of what I mean by reliable. But you're right. I mean, reliably and consistently store data allow you to manipulate it, right? You know, Margot, who taught me this class, did a lot of work on file systems. And she used to say that, you know, consistency bugs in file systems were the worst kind, because when somebody's data, when you actually caused data loss on someone's system, they not only had a reason to come hunt you down, but they had enough time on their hands, right? To just sort of ruin whatever they were working on, right? Yeah, and then have a name, right? So we think of naming, right, which allows me to identify. I mean, I guess if I only had one file, I wouldn't need a name, but that wouldn't be very interesting. That would be a disk essentially. So I have a name and some contents, right? Great. And what do we expect about files, right? We already started this, right? They shouldn't change unexpectedly, right? If nothing happens, the contents of the file should remain the same. And I should be able to change them in predictable ways, right? And have those changes persist, right? And you know, these are very basic file system requirements, but there's still plenty. This is a hard problem, right? And you can see this by, I mean, if I had looked this year, I'm sure I could have found another one of these, right? But there are still file systems deployed that have consistency issues, right? That will, in certain cases, lose data, right? Or corrupt information. And part of the reason why this is a hard problem is because of disks, right? So part of the introduction to disks is designed to set the stage for all this GUI, moving parts, failures, wearing out sort of stuff that makes building reliable file systems on top of these unreliable, failure-prone devices very hard, right? All right, so what else might mean, you know, other than the contents of the file, which is sort of what the file exists to store, what else might we want to know about it? Yeah, Mac. Okay, the size, yeah, that's a good thing, yeah. Yeah, I mean, what we think of as permissions are really file attributes, right? If I didn't store permissions, I would just have an ultimately permissive file system, right? You could do anything to anything, which would be interesting. Yeah. Last modified time, right? What else? Yeah.
The owner or the amount of data.
Yeah, so the owner, right? Maybe the group if you want to get all sort of Unix. Yeah, what else?
Physical location on this.
Oh, interesting. Physical location on a disk. It's not usually exposed by these file systems, but that could be interesting. Yeah, it's true. Format, yeah. So something, so this we mostly got, right? Timestamps. Who is allowed to do what to the file, and to some degree the owner and the attributes that we associate with Unix files sort of bind both of these things together, because I do permissions based on identities. And yeah, sort of things like the file type, right? How do a lot of systems encode file types? Yeah, it's really, this is possibly one of the most broken things about modern computer systems, right? We fixed a lot of problems with modern computer systems, but extensions are still a terrible, disgusting hack, right? Like, I mean, I'm sure you guys have had this warning on your system where it's like, you're changing the extension of the file, right? Do you really want to make this into a PNG? It's like, I don't know, What is a PNG? How many people have ever had to Google on the line to find out what a particular file type is? Like, what is this thing, So, yeah, I mean, file extensions are kind of terrible. But when you start actually thinking about more specific types of files, these other attributes become a little bit more interesting, right? So again, this is all based on my my early love-hate relationship with my MP3 collection. But MP3s, like audio files, what other attributes are associated with those files? Yeah. Yeah, he picked a boring one, right? Bit rate, the artist, the song name, the genre, who put a genre tag in there? As if we could agree on that, right? Yeah, so, the date it was recorded. I mean, these things are at least facts, right? Genre is now we're getting into editorializing about the, and there are file systems that have addressed the question of where these attributes should be stored in a variety of ways. Where are these attributes stored on a lot of systems today? Yeah, Gabriel. Yeah, so at some point people just decided, let's just bury these in the file itself somewhere, right? So we'll actually modify the file format to store this information. You can imagine there's a lot of gross things about doing it that way, right? Other systems have actually had them in separate files, equally, if not more terrible. Because now I have two files that sort of have this weird relationship with each other that I have to keep together. But there are files, and actually I think there eventually was mainstream support in a lot of file systems for defining attributes that are maintained by the file system, right? They're not maintained within the file. And this allows you to do sort of cool database-y-like things, right? So if I can give a file a name, and the file system knows what the name is, then the file system can help me run a query over the entire file system to find certain kinds of files, or files whose names contain certain things or whatever, right? Sorry, name is a bad thing. If I could give the file an owner, right? Or no, owner's bad too. An artist, right? I could say, find all file types of MP3 with artist that's equal to Britney Spears or whatever, and delete immediately. I have some Britney Spears. So each one of these design decisions, I don't want to go over this in detail, have, so the MP3 ID3 tag, right? The nice thing about putting it in the file is it moves with the file. The con is that now I have to have every program that reads this file understand this file format, and if I want to change the format, that's potentially sort of ugly. iTunes database stores, if you guys use music players, probably stores a lot of information about the files that you have. This can be maintained separately. For music, what still frequently gets stored outside of the file? Yeah.
The album art.
Yeah, artwork, right? For some reason, I don't know. It's weird. And this stuff doesn't move. It's difficult to sync. And then finally, attributes are nice because they're baked right into the file system. But this also doesn't necessarily move with the file from computer to computer because it's stored outside the file contents. All right. So you guys are probably familiar with this interface by now, right? Since you've spent a little bit of time working on implementing it. And when we think about how the operating system establishes relationships and connections between files and processes, one thing you guys may have wondered by now is why do I need open, right? Why have an open call in the first place? What would be the alternative to using open and close? What could I do? Yeah.
You could just kind of load and store to the file directly. You wouldn't have to go through this.
What would I have to give the load and store? Well, load and store, read and write. Let's say I just wanted to get rid of open and close. Just use read and write. What would I have to give read and write every time?
Location of disk.
Yeah, path name. But I could do that, right? What's wrong with that? Would that work? Yeah. Whatever. Yeah, the process can store the offset, right? That's actually a Unix. I'll come to that in a minute. It's a Unix design system. Yeah, so to some degree, the reason that there are some good reasons that the operating system wants to establish these relationships between processes and files, right? One is that it's possible that I can improve performance in certain cases if I understand patterns of access to the same file. And having open means that I know that a particular process is using a file, and I might be able to do some things in order to try to optimize file performance. But also, there's times in which I actually want to be able to provide guarantees to processes saying, you're the only process on the system that has this file open. In what case might this sort of guarantee be very difficult or dangerous to provide? what kind of file system? You guys probably use this kind of file system frequently, even if you don't always know that you use it. What about networked file systems? Let's say I provided an exclusive open on networked file systems. And then your laptop disconnects without closing the file, right? So who gets to open that file again? I don't know. I mean, there's hacky ways to fix this. You know, you have heartbeats or whatever. But yeah, so this causes problems on network file systems. And actually, some network file systems actually have no real concept of open and close, right? They don't even implement open and close. You essentially have to tell it every time you perform a read or write what the actual file is that you want to modify. Right? All right, so and, we talked about, somebody brought up the fact that I wouldn't know what the offset is. Who cares? I mean, this is just a convenience. Don't think that this is like a real deep feature. I could certainly have the process just tell me every time it wanted to read or write what the offset was, and that would work fine. Hello. And yeah, the relationships. Okay, you guys know this stuff by now. Okay. Yeah. All right, so let's talk about file organization. I don't need to cover the file interface, do I? You guys, yeah, we did this before. So early file systems, in order to uniquely name a file, the file has to have a unique name, right? So that the file system knows what I'm trying to open and not just whatever, right? So here's one way to solve this problem, right? And there were early file systems that essentially worked just this way, right? So here's letter to mom, here's letter to my wife, dog. I wrote another letter to my wife, another one. Yeah, and actually there were early file systems that provided essentially a flat namespace, right? So imagine if every file on your computer was in one folder. It get confusing fast, right? And so, we've built these sort of you guys are so used to hierarchical file systems, right? It would be really interesting to have been around during the dawn of hierarchical file systems, right? It was probably a lot of fun to create folders and move things around. Now we're just all used to this, right? It's sort of baked into our systems, we don't even know it, right? And this is to some degree, this is a nice organizing principle. It seems to have either one of two things is true. Either this matches some way that we think about data and information, or we've learned to use this tool to do things that we want to do. Right? To some degree, it's not perfect. It's not as easy to use as search, but it does work. Right? And one requirement of this is that each file should be stored in one place. Right? We still want each file to have a unique name. Right? But now the name has these semantics to it that encompass both uniqueness, right? A unique path name, and structure, the structure of the underlying system, in this case being hierarchical, right? So let's talk about the implications of location, right? So first of all, I need to be able to navigate the hierarchical file system, right? If I build a hierarchical file system that no one can find their way around, this is a problem, right? And this introduces this concept of a directory, right? Which the file system now has to support. Before hierarchical file systems, I didn't need directories, right? All I needed to support was files. Now I have this interesting new feature that the file system has to figure out how to support, right? And then, location in a hierarchical file system has, if you think about it, the canonical location of a file has the canonical name of a file has location embedded into it, right? And that location can either be relative to where you are, or it can be absolute. But most file systems, I should say most, I think it's a requirement of hierarchical file systems that you have some sort of canonical name for each file, right? And this leads us finally to this tree requirement, or this tree feature, right? File systems that provide hierarchical namespaces are organized into acyclic graphs with a single root, right? So they're known as a tree. Why is this? You guys have probably used file systems like this. But why do this? Why do I need a root? Why can't I have multiple roots? Or why can't I have no root, right? What does this provide, right? So okay, so let's say that we don't have a root. This file system does not have a root. What is the name of this file? This one. So here's, let's say I pick this as my root. It could be you used to love well, or you, me, love well, right? Or actually, it could be you used to love me, you used to love me, you, me love well, right? So this file now does not have a unique name, right? If we define the name as the way to reach the file from the root, right? And this is because now here, again, I could start anywhere, right? Love to, use, you, me, love well, right? Or you used to love me, love to, love well, right? But so even after picking a root, I still have this problem. I don't have a unique name for this file, right? If I create, if I trim this, right? So now I've eliminated the cycles. And now, essentially, what I've defined, that I can define the name of this file uniquely, which is the shortest path from the root to reach the file. And this is the, the single canonical name is the shortest path from the root to reach this file. There are still an infinite number of relative names for this file, right? So here's my canonical name. Here's one relative name, right? You used to love me up well, right? You guys are used to using these features, right? Here's another one. These are kind of fun, right? So this is, I started here, love me, well. And I just like this poem, which is why I used it for this example. So you guys can look at that online. All right, so let's talk about now that we've sort of come up with the requirements for this particular abstraction, let's talk about the design goals of the underlying file system stuff, right? So one thing I clearly need to be able to do is when the user gives me a name, I have to be able to find the file. And I want to be able to do that quickly, right? Because the user is waiting and they get impatient, right? I want to allow the contents of files to change, right? And doing this, if you think about the contents of files changing, it's a pretty clear line to the size of the file changing. And within the hierarchical file system, I also want the file to be able to move, right? So I want it to be able to grow, I want it to be able to shrink, and then it should be able to be moved from one part of the system to another, one part of the tree to another, right? I should be able to, and really I should be able to rename the file. That is essentially what that operation means, because with my hierarchical file system, naming and location are sort of bound up together, right? I also want to make access to single files fast, because a lot of certain types of I/O go onto single files. But I also want to try, if I'm clever and intelligent, and this gets to all the sort of fun engineering and interesting design goals of file systems, to detect patterns in the way people use files, right? Put cluster-related files in places where I can get to them efficiently on the disk, right? And then finally, and again, maybe this shouldn't have been 0.5, it might have, 0.1 might have been more effective, but I need to try to do as much as possible, to make sure that changes to the file system persist despite whatever happens to the underlying disk. So if my disk fails, and it's not just disk failures, what other types of problems do file systems encounter? What other kind of failure of sorts might a file system have to deal with? Yeah? Yeah, okay, but again, this isn't a disk failure. This is a yeah. So I might need to make that's a good one. I might need to make sure the file system remains consistent, right? Even though operations are canceled or might fail in certain cases. But what else do people do sometimes to the computer? Yeah. What's that? Okay, so now we're getting into features, right? I might want to prevent people from doing dumb things like accidentally deleting files. What else? Yeah, like I trip over the power cord, I knock the computer over. the dog sat on the computer and hit the power button, whatever, right? I mean, sudden changes, particularly to power state, right, that can cause problems with maintaining the file system. And there's two related goals we'll talk about here. One is trying to make sure that all modifications of the file system are eventually reflected on disk and are stored. The other is trying to make sure that the file system itself is consistent, right? Because file systems, as we'll start to talk about, involve a lot of on-disk data structures which can get corrupted quite easily. And corrupting those data structures could mean that all the data is there, but you just can't find it, right? Or the file system doesn't know where it is. And as we start talking about file systems, there's this common set of features, right, that sort of coalesce fairly early in file system design that all these file systems support, right? They all obviously support files, and a lot of them have support for attributes and permissions and associating those with files. And they all allow you to organize those files into a hierarchical namespace, right? So the fascinating thing from the perspective of file system design is what the on-disk data structures look like. Because the interface of the file systems is all pretty much the same, right? I mean, if I sat you down in front of a computer and I said, on one mount point is an ext4 file system. On the other mount point is an ext3 file system. Can you tell the difference? I mean, you probably run mount, right? And then you would tell me which one was which. But if you were just sort of poking around in them and using file system features, you wouldn't know, right? They're pretty much the same. So how do we implement hierarchical file systems on top of disks, right? So you have to think about the file system itself as providing this interface and set of abstractions. But then really what ends up happening is the file system uses disk, reads and writes to disk blocks, okay? And we can start out by just dividing the disk blocks that are used by the file system into two categories. There are data blocks, and there are what are called inodes or index nodes, right? So what do you think data blocks contain? File data, right? Like data that's actually part of a file. So what do inodes contain? Anything else, right? Almost anything else. Anything so if you think about the file system, there are blocks on disk that are used to store file content, and then there are blocks on disk that are used entirely for file system data structures and other sort of information, right? And that's sort of a nice way of thinking about how this is organized. The overhead, right? So to some degree, if you think about your file system that you would install after you. So what is formatting a disk, right? Now that you know this, what does formatting a disk entail? You have the disk starts out. It's this big bunch of blocks, right? What does formatting a disk do?
Just mark it so that the data can be overwritten.
No, like if I take a drive and I format it on my computer system, what am I actually doing?
If you're doing a quick format, you're wiping out all the inodes.
Well, forget the quick format thing. Yeah, I don't know why there's even a non-quick format. What's that?
You're overwriting a data.
I'm going to overwrite some data, but what am I going to write? What type of information is being written during a format? Yeah. Yeah, I'm basically creating a clean and empty data structure for the file system, right? This normally involves writing a certain amount of data to the actual disk, right? Not necessarily that much. Maybe if I do a long format, actually I want to erase all of the other data. It's not usually necessary, right? What I'm doing is I'm taking I'm taking those disk blocks, I'm giving them to the file system, and I'm saying, set up whatever data structures you need to use the rest of this disk, right? There's some overhead involved in this, right? So if you look at the disk size, so one of the things that happens, is you buy a disk that's a terabyte, and you format it, and suddenly you have, 982 gigabytes of space left, right? Some of that difference is because disk manufacturers don't use power of 2 arithmetic, right? So a terabyte is actually 1 trillion bytes rather than an actual terabyte, right? But part of it is because formatting takes up space, Right? The on-disk data structures that are used by the file system are not invisible, and they do consume part of the disk. Right? So if you think about the design requirement we had for file systems, there's a couple of things that make file systems different from each other. Right? One of them is simply how they organize blocks on disk. Right? So where do you put data? Where do you put metadata? How do you find things? Right? Why? So going back to what you guys think about know about disks now, why does on-disk data structure, on-disk layout matter so much? Why would this be less interesting if you were implementing the file system in memory? It could still be a little bit interesting, but what's interesting about disks? Yeah, Jay.
Memory is random access, but for disk, you actually have to spindle it to wherever, you move the arm to wherever your file system data structure is, which could take more time.
Yeah, so disks have locality, and that locality actually matters quite a bit, right? Having to move the arm around, having to, to some degree rotational latency, but it's really, a lot of it is moving the heads back and forth. That matters, right? And so one of the reasons that file system disk layout matters is putting things in a certain place has performance implications, right? It means that there's a certain amount of time to delete a file. There's a certain amount of time to read the contents of a file or to traverse a directory or to do things like this, right? And if I'm clever and I put things in a the perfect place on disk, it's possible that I can optimize performance per particular workload, right? So part of that also has to do with data structures, right? The data structures that file systems use to actually organize and find information about the files, right? Where is a particular file located? Where are the data blocks, right? I mean, when you read a file, that's what's happening under the covers, right? Is that the file system has to figure out where are all of the data blocks for this particular file, right? And finally, something we'll talk about as we talk about each individual file system is crash recovery, right? What do file systems do to prepare themselves for crashes and to try to make recovery fast, right? Because there's two related issues here, right? One is, if you crash, how much data are you going to lose? The other problem is what? So you tripped over the plug for your computer and it turned off. What are you going to do next? Plug it back in, turn it back on, and then what do you not want to see? Well, yeah, okay, you don't want to see that, right? But you also don't want to see the file system being like, rechecking file system like 2 hours remaining, right? So it's not just crash recovery, right? It's the speed at which I can recover from crashes, right? So it's possible that if I checked every block on the disk, I could completely recover from a failure. But if that takes 2 days, right, and you're talking about a really, really popular website, it's probably not acceptable, right? So recovering from failures quickly. I remember one of my I sort of fat-fingered a format once when I was a kid, and one of my drives with, again, it's all about MP3 collection, but that I had all these MP3s that I painstakingly collected and organized, and I lost them. So I bought this tool to help me recover the drive, and it ran for a couple hours, and it was like, I found all these files for you, and I was like, great, and there was a small number of files that it couldn't locate, right? And I was like, oh, whatever, it's like 10 or 12 files, I'll take it. So I started listening to some of those files that were recovered, and where do you think those 10 or 12 files were? Just little bits of them here and there, sprinkled all over the place, right? So it's like, listen to a bloop, little bit of another song, and it just kept going, right? So yeah, anyway, it was sad. I had to throw everything out. I just couldn't handle it. It was too weird. So again, and just to give you more appreciation for this, file systems, big complex data structure on disk blocks, right? And like most complex data structures, updating file systems requires changing a lot of different things, right? And so keeping files consistent means figuring out, which parts of the file system did I change, and trying to make sure that a set of coordinated operations all happens at once, right? Because I can lock the file system, in a synchronization way, but if the user trips over the power cord in the middle of me holding, who cares, right? Like the lock doesn't help me, right? The lock won't keep the power on. Just as an example of this, right? So let's say I want to write, let's walk through an example of writing data to the end of a file, okay? I have a file. That file consists of some data blocks on disk. Now let's say I want to append to the end of the file. What do I need to do? I call append, right? What does append do? What does append need to do? Yeah. Okay. Okay. I mean. Okay. Oh, actually, this is a great thing. So let's say I find the end of the file, right? So I find the last data block in the file. Is that helpful necessarily? So let's say I locate the last data block in the file on disk. Yeah.
So you have to check the next one to see if there's a file there? Some other data?
Yeah. Who knows what's next to that file, right? But so generally, if I want to append, I want to add data to a file, what do I need to do? Find empty disk blocks, right? If there is space on the disk, right? But this is the first task. I have an allocation problem. I need to find empty disk blocks, right? And remember, if I care about where things are, I might want to find empty disk blocks that have a certain relationship with the file that I'm appending to, so that things don't end up all over the place and the head doesn't end up running all over the disk and you hear that terrible grinding noise. Yeah, so then I have to somehow figure out how to make my data structure understand that those disk blocks are now part of this file, right? Now I have an attribute, potentially, and these really aren't in order. These are just sort of all things that need to get done. Copy the disk, copy the data into those disk blocks I found, which could involve seeking around. And from the perspective of a process, it's important that all of these happen synchronously, right? There's this sort of atomicity requirement that we're trying to, So for example, let's say that I did 1, 2, and 4, and then the power went out, right? So what would be the problem? Yeah.
When you reboot, it would appear that the file didn't roll at all. It was its original size. You didn't append anything to it.
How hard would that be to fix? Yeah, that's probably an easier one to fix, right? So if I drop 3, I could still just look at my on-disk data structures and use those to make sure that the attribute, because the attribute's just a hint, right? To some degree, I should be able to figure out how large the file is from the disk data structure, because I need to be able to find all the blocks, right? What if I do 1 and then I don't do 2? Or let's say I do 1 and then the system crashes. Now what problem do I have? Yeah. Yeah, I've got some data blocks on my system that are, who knows, And actually, how many people have ever found stuff in lost and found on their system? It's a slightly different. What's that?
I have a more fun problem.
What's
My
that?
users got deleted, but didn't fully get deleted. So if you try deleting it, they'll tell you can't delete it because you're not that user, but you can't log in as that user. So it's just there forever.
Interesting.
Yeah.
But if you've ever, on the file system, if you've ever found something lost and found, it usually means that something like this happened. Right? There was a file on, and actually usually what that means is that there was a file on your system that the file system didn't know where it was supposed to be, right? It was just hanging out on disk, wasn't attached to any directory, and so the file system was kind of like, don't know what to do, right? I'll just put this into this weird, funny directory and let you figure out what the actual problem is, right? But you can imagine that if failures occur at various stages in this process, I can have a corrupted state. And remember that performing all these activities actually requires touching a bunch of different blocks on the actual drive, right? So I've got to seek around, I've got to touch a lot of things, and in the process, something else might happen, or the disk could fail, right? All right, I'm done for today. We'll pick up on Monday and talk about path resolution. Good luck with assignment 2.